So one of the things that you did say that struck me a lot.
Speak right into the microphone.
That you said that struck me as very important, but didn't elaborate a lot on, is you showed these two diagrams of whether we could infer the past and future equally, or whether because of randomness, those gave very different interpretations about past and future. Yeah, that's the figure that I'm thinking of. And so biologists, I think, do see the influence of that, and it's because randomness is extremely important in biology, and I guess it is in certain areas of physics. In physics, it seems like reconciling the classical model and the quantum model, they seem like almost, at least to a layman, and I'm outside physics, they seem like such totally different scales that they're hard to find the intersection. Whereas in biology, the intersection between random and predictable processes lies right at the heart of our theory. They're processes, in particular like mutation, which we say is a random process. But we actually have to be very careful in the sense that we mean it's random. We don't mean it's uniform across time. We don't mean it's uniform across organisms. We mean it in a very specific sense that the organism that may or may not be mutated is not controlling what its next state is going to be. Natural selection, Darwinian evolution, the key point there is that it's a systematic difference in the performance of organisms to produce fewer or more offspring across generations in response to environmental selective pressures. So to me, that kind of interplay is extremely important.
So I wrote a paper with Anthony, actually, and Matt Johnson, where we talk about downward fluctuations in entropy, and there's a statement in there that says that tiny downward fluctuations in entropy are crucial to the functioning of living organisms. Yeah, I think so. This speaks exactly to your point that whereas we quantum people need to work hard to get at the intersection of the classical realm and the quantum realm. In biology, you're always right on that edge of the importance of both the structure and the randomness.
And I think the way physicists look at things with so many particles essentially identical, but biologists, everything is different. Darwin's theory rests on the idea of variation. And so we're stamp collectors at one level, but our theory also depends on understanding sort of not just the sort of ensemble properties of life on Earth, but the details of all the transitions that have ever happened and ever could happen. And so I think that gives us sort of a sense of the incredible path dependence and the likelihood that anything would be reproducible at even a fundamental biological level seems very unlikely.
So I thought one of the most interesting points you made was that time is fundamental and space is not. And so I study time subjectively. I'm interested in human memory. And a few years ago, I wouldn't have found that particularly interesting or thought-provoking in the way that I did today, because we've been looking for this sort of neural substrates of this idea of sort of projecting yourself to the past and remembering versus projecting yourself to the future and thinking about the future in a subjective way. And certainly they feel different, and the past seems like it's restricted in a way that the future is not. But we can't find any kind of evidence that there's this fundamental distinction in the brain using fMRI. And we in other labs have been looking for a few years now. For a long time, psychologists paid much more attention to the past and remembering than thinking about the future. So anyway, this idea that we have this mental set of sort of going backwards or going forwards is something that intuitively makes a lot of sense, but it doesn't seem to be too much different from a mental set of just sort of trying to think or imagine. And so the idea that time is so fundamental and space is not so much, we can readily find the influence of spatial configurations neurally, but the sort of mental set of traveling in time is something that we haven't yet been able to find. So I mean, we're still looking. It seems like it just has to be there, but
right.
It's been elusive.
Yeah, yeah. It's hard to find time in the brain. This is something I definitely hope to that we keep talking about. Yes. All right, Steve, you're next. All right, Phil, you're next. Steve is looking at you.
Okay, so you told me before this session that I was here to contradict you. So I've been making a list of the things you said.
I'll sit down.
So I think there are a couple of things you left out. the question of what's fundamental, of course, depends on what the meeting's about. It reminds me of a story that that I saw in a newspaper a long time ago, that an accelerator had been built, I guess, outside Oxford in the UK, and the job of this accelerator was to smash words together in order to find the fundamental units of meaning, which was considered to be the most fundamental question that man had ever asked. Of course, the fact that it was close to Oxford tells you who wrote this. Obviously a philosopher at Oxford. So, I mean, I think that it's important to focus on some philosophical questions, and I'll come back to those. But I think, let me just run through the list. First of all, you assume that quantum mechanics is correct in everything that you said, and I think that there's very good reason to suppose that it might not be, and I'm sure that'll come up. I think that people who are worrying about time have to worry about that possibility, if not likelihood. I think that, well, something that I'm going to talk about in this talk that you asked me to give later on is to do with decoherence, which I guess you have not discussed. You preferred to talk about irreversibility, dissipation, and so forth. But of course, many people, when they talk about time's arrows, they put in there a quantum mechanical arrow, and so I guess we'll be talking about that. I think that's actually rather crucial. I think another thing that, well, okay, so I completely agree with you that one should distinguish between complexity and entropy, and that one should be asking very seriously the question what one really means by life. And I guess I didn't really like your definition.
I didn't have a definition.
Well, you said it's what matter is if it keeps on moving long after it's supposed to stop. And from this I infer that this boat is alive, and that perhaps the universe is alive, and we immediately realize that something may actually be doing that, but it's not doing it because it's alive. Possibly it's doing it because something that was alive, possibly a long time beforehand, designed it and maybe even built it. But then that gets you onto rather dangerous ground, because if you are going to now say that something that fulfills your criterion of life may not really be live, but is in fact doing this because it was designed by an intelligent designer, then I think you can see where you might be going. I think it's another thing that was not discussed by you, which I think is really important and is becoming more obviously important in the last couple of years, is the clear role that quantum mechanics has to play in some of the more important processes that are involved in life, and which no doubt play a role in the origin of life, whatever that may be. And so I'd like to finally remark that I think there are some important philosophical questions here, which you didn't mention. So I'll just single out two. One is the question of what you really mean, the distinction that's been made by physicists between system, metasystem, or between subject and object, and the ensuing questions that gets you into about self-reference and so forth. And this, for a physicist, translates into concrete questions about whether one should really be relying on a framework involving Hamiltonians, effective Hamiltonians, and so forth. And it's quite clear that to anyone who's working either in string theory or on decoherence, that there are very severe problems associated with that way of doing physics, which of course is what we've been doing for 2 centuries now. So that's all I have to say.
Well, as opposed to, what is the other way?
Well, unfortunately, we don't have one. I mean, many of the string theorists will tell you that they have one, but since they all have different ones from each other, then it's clear that at least n-1 of them are wrong.
Okay, I actually don't disagree with that much, except I think the quantum mechanics is right. So.
Well, okay, let me ask you, are you talking about non-relativistic quantum mechanics, which is what you wrote down? And if not, what quantum mechanics are you talking about?
I wrote down quantum
You wrote down Schrodinger's non-relativistic equation.
That's perfectly relativistic, that equation.
Excuse me? don't think
that's
so.
just as true in quantum field theory or quantum gravity.
No. What do you mean by H?
The Hamiltonian.
Yes, but what do you mean by that? What do you have, an ultraviolet cutoff? Why is it there? Is there anything outside that ultraviolet cutoff that's involved?
No.
Thank you.
So the question you asked us is, was there anything important you left out? And here's one stab. If you'll go back to the slide you had up, which starts with the intuitive understanding of time, by which I'm going to mean the following. We have these global sets of simultaneous events, and the intuitive notion of the passage of time is that these sets of events occur successively, one after another. Now it seems to me one of the first things that we learn from Einstein in the special theory of relativity is that when you have a couple of events that are time-like separated, right, if they're connected by time-like lines followed by idealized clocks, the time between the two events is actually path-dependent. That tells me that there's no notion of a global passage of time at all. The notion of passage of time, if it's intelligible, has to be local along a time-like curve connecting time-like separated events. And if 2 points with respect to that, I find that difficult to get into a kind of a clear focus with the intuitive global picture. But secondly, I find there's a kind of an odd duality. I mean, if the puzzles in quantum mechanics, or some of the puzzles in quantum mechanics, are that there are events that we think certain kinds of connections ought to be local that turn out to be non-local. But in thinking about time, our intuitive understanding is global, but it actually turns out to be local. Then, although I have nothing further to say about it, it seems to me that there's an odd duality that doesn't seem to me coincidental.
All right. So let's open it up to the audience. Is there anyone, well, actually, sorry, I should say, to the panel. Is there anything else that you really wanted to say? This is your chance just to say anything at all that you wanted other than Philip.
You didn't mention the word experiment once.
Yes, I know, but I mentioned the word observation. Doesn't that count for anything?
No, that just shows that you're a cosmologist.
Yeah, I know. I will take that fair point. Fair hit. Okay, yes, there's a question, David.
One of the things we know when you write down that configuration space times time framework is even to speak about a configuration space, I've got to foliate, I've got to say, well, this point is atom number 1 is here, exactly when atom 2 is here. Of course, that's not relativistic covariant. We know how to do field theory modulo Philip's worries about the ultraviolet cutoff in a way that is covariant, but the very fact of moving to field theory puts us back in a framework where space and time seem to be rather more on an equal footing. And I imagine you'd agree that in field theory, space has been a bit less relegated than it turns out to be in quantum mechanics.
He was also getting at something of this point. When I am saying, so when I write this equation, which is Schrodinger's equation, I said, look, there it is, time. The letter T appears in this equation several times. But we all know that relativity is pretty good. I wrote a book about relativity. I think it's a good theory. And in relativity, space and time are treated on an equal footing. So how does one reconcile this? And so I think my personal attitude, which is certainly I'm willing to have my mind changed about this. But my personal attitude is that you should start with this equation. You start with Schrodinger's equation with some space of possible quantum states and some operator, the Hamiltonian, that says how you evolve through that in time. And from that, you should derive the existence of space and matter and all the symmetries that are associated with them. So it is certainly true that there are different ways of slicing the universe into moments of time in which you would get what looked like a different time evolution, but you realize, oh, it was really just a change of variables from the original one that I got. And but I don't think that you should start by worrying about those particular set of invariances and then try to fit them into quantum mechanics. And the best evidence I have for this is again in the holographic principle, you believe that there is a duality between two different descriptions of nature, which have different number of spatial dimensions in them. So there's different symmetry groups associated with those two spatial descriptions of nature. But time is treated more or less the same in both of them. So I think that space and the Poincare symmetries that are associated with it should emerge out of a Hamiltonian once you go to this low energy effective regime that Philip was referring to. But I admit that there's a lot of work to be done with that. I don't think it's a simple thing. George.
Sean, could you go back to your statement about quantum mechanics? You had a thing about the arrow of time.
This one?
Yeah. The future observations are not predicted deterministically. Don't you mean they are predicted deterministically?
No.
I think I mean they're not predicted. I don't know whether the...
Oh, sorry, I got you right. Yeah, sorry,
Okay, good.
So what you're not pointing out there is that once collapse of the wave function has taken place, going to the future, they are predicted probabilistically. Going back in the past, there's no prediction whatever. And I think that's an absolutely fundamental asymmetry there. So in quantum mechanics, going forward, you get a probabilistic prediction. Going backwards, there isn't any prediction at all.
So this is an excellent point that should be discussed, and I completely disagree with what you just said. Or rather, there's certainly a phenomenon which is true, that if we have a quantum state and we observe it, we can probabilistically say what the outcome of a measurement is going to be like. But if I give you a quantum system and say, I've already observed it, what can you tell me about what it was like, then you can't say anything.
Yeah.
So I personally don't believe that that's a reflection of quantum mechanics. I think that's a reflection of our knowledge of the world, which comes from the same place as all of the differences in our knowledge of the past versus the future, namely the low entropy of the early universe. And I think that this shows up in something that Jeff Tollickson was talking about and worked on with Aronov and other people about time-symmetric formulations of quantum mechanics. So my personal belief, which does put me in the minority, I think, so you're welcome to disagree, is that quantum mechanics is perfectly time-symmetric. But the way that we use it in the real world is manifestly asymmetric, and that's because we know that there's a low entropy boundary condition in the past, but not in the future.
Okay, so when you say quantum mechanics, do you include something about collapse of the wave function or not?
I do.
Yeah, then I don't
I'm obviously very sympathetic to this general strategy of sort of blaming everything on the initial low entropy state of the universe. But the content of the mystery is supposed to be, look, according to this scenario, the world started out in a highly improbable state, okay? Or to put it in a less tense-dependent way, the trajectory of the world is a highly unlikely trajectory, as we see. Because if you put it that way, there's a puzzle about where one gets one's ideas about what's likely and what isn't. If somebody says the trajectory of the entire world is very low probability, is very unlikely, it seems like a natural question to ask, gee, where is it that you're getting your ideas about what's likely and what isn't? Certainly not from the world, okay? Certainly not from looking at the world, because you have some idea of what's likely and what isn't, on the basis of which you're ready to say, the world as a whole, the entire history of the world, is extremely unlikely. Now, there's a story that all of us can tell about where this comes from, which is that there's a notion of likelihood, there's a notion of probability that played an important role in physics at the end of the 19th century, which was sort of a priori, okay, which had to do with principles of indifference, in terms of which the laws of statistical mechanics were originally formulated. But most people who think about probabilities think that on reflection, that sounds crazy, okay? Probabilities, after all, are things that have some connection of some kind or other with the frequencies with which things actually happen in the world, okay? And it feels crazy to think that claims about such frequencies could be derived a priori, that claims of about such frequencies could be derived without any reference whatsoever to our observational experience of the world. If we do dismiss that as crazy, and if we say probabilities, like any other fundamental laws of nature, must come from observations we make about how the world is, they're not logically necessary or something like that, there's a puzzle about how one could ever find oneself in a position of saying, we've got a puzzle here because the world as a whole is unlikely, okay? It would seem like if you're in a position like that, you got to say to some guy, where did you get your idea of what's likely and what's unlikely? If the guy says, I got it a priori, you say, that sounds like a bad place to get it. And if the guy says, I got it from some theory, it seems like the right thing to say is your theory has just been trivially refuted by the world, okay? Where else might we get it? How might we find ourselves in a position to say coherently and seriously, we got a problem here because the world as a whole is highly unlikely?
I think it's an excellent question. I have something to say. Phil, do you want to go first?
I'd like to relate that to another question, which to me is actually very closely related. People often get into discussions about things like the anthropic principle, and it's remarked that there's a remarkable coincidence of circumstance required to produce things like us in the universe. And then the counter argument to this is to say, look, you can go into a giant building which is full of money, and you can pull out one single bill and find that it's got a certain number on it, and then say, wow, isn't that amazing? Who would have predicted that you would have gotten this number? And of course the point is that you have no idea what all the other universes are going to be like. All you've got is this theory. And so to say that the universe is unlikely assumes that you know a priori what all the others are going to look like, and you can say a priori that they're equally likely, and so on and so on. And of course, theoretical physics right now is utterly incapable of saying almost anything about the world a priori, about just one example. So for theoretical cosmologists to be telling us what the other 10 to the 500, which is another number they pull out of the air, universes would do, is kind of ridiculous.
How would it ever possibly make sense to make a statement like, the universe appears unnatural, right? How does the universe appear unnatural? How does nature appear unnatural? But I think that there is an answer that we're, pretending we don't know, but we actually know. There's several answers. One is, it might be completely wrong to think this way. It may simply be that there is one universe, and this is what it is like, and there is no other mechanism that makes it this way, that we're just stuck with it, and it's a nomological fact. So that's logically possible. Personally, I think that the low entropy of the early universe should be taken by us as a clue to something deeper, because we don't claim to understand the early universe. It is what in some measure is a remarkable fact, and therefore might lead us to think something smarter. The measure that gives us the statement as a remarkable fact is what David alluded to, some indifference over all possible microstates compatible with our current macro state. And that is clearly where this intuition comes from, that the early universe being low entropy is something that needs to be explained.
Sure.
But
can I follow this up just for
yes.
Slide? Look, tell me the difference between this and the following question. Somebody says, suppose Newtonian mechanics are true. Suppose the Schrodinger equation were true. It doesn't matter. Somebody says, God, look at this. Everything's obeying F equals ma. What are the chances of that? You know how many other laws we could write down? Okay? There's something fantastically unlikely about our universe. It couldn't be like that. We've got a mystery here. Look at the space of possible equations of motion. Okay? It's enormous. Okay? What are the chances that it could be F equals ma? That's a question that we would usually dismiss. What's the difference between that puzzle and the thing you're puzzled about here?
So David's question is, what is the difference between being surprised at a particular law of nature and being surprised at a particular configuration or trajectory of the universe?
If laws are just supposed to be things of a pretty simple and highly informative nature that are true about our world, claims like the past hypothesis count as laws too.
No, that's fine. So what I was getting at was the fact that clearly the reason why, psychologically, we do think that the low entropy of the early universe presents us with something to be explained is because we are familiar with subsets of the universe that have entropy and that do have frequencies associated with them. And it is also true, I completely grant, that once you think about it carefully, you realize that it's not okay to reason from subsets of the universe to the whole universe in this way, because we don't see an ensemble of which the universe is a member. However, we can then say, look, there's lots of things we don't understand about the early universe. Let's try to understand it. Let's invent inflation or Euclidean quantum gravity in the wave function of the universe. And I would say that we are, at least at the theoretical level, then faced with, or given rather, an ensemble. We have theories of what the universe could be with measures on them. And sometimes they're well-defined, sometimes they're not. We have no theory that is well-defined and says that universes like the one we see are the ones that we should find ourselves in. So my short answer to your question would be that as we understand quantum gravity and cosmology better, we come to a place, we come closer and closer to making this a well-defined question within a theoretical framework. And it's not like all of the different proposals answer this question in an easy way. It's more like it gets harder. So I think you can't interrogate the foundations of this question and take it too seriously, but you can use it as a guide to trying to do better. That's all I would ever say. Yeah.
I think we're already treating this, at least many of us, as a simple observational question. Whether there's a problem with the low entropy of the early universe, you can translate that into a conflict between a theory and the data. There are some theories, like if you say the universe is a closed ergodic system, that conflict with the data. It doesn't matter whether you worry about the whole universe or not. They simply predict that we should see something else. We should not see something that's compatible with a history where the universe started out low and the entropy is slowly getting larger. We should be seeing ourselves as a rare fluctuation in the messy universe. So it's a very, ultimately, it's like what we do any other day. The other thing was I wanted to sort of play devil's Philip Stamps advocate.
I came over from the docks.
I didn't understand anything you said about string theory, but I think it actually supports what you said in the criticism of Sean's support for time as a truly fundamental thing that isn't going to go away. So first of all, I agree with you that time, the question of whether time is fundamental is very closely related to whether quantum mechanics is fundamental. But I agree with you that we shouldn't take for granted that quantum mechanics is fundamental. And I think there is some evidence that, there were opportunities when we could have discovered that time is fundamental when we didn't. So a question where both time and quantum mechanics become in danger is near singularities. If you fall into a black hole or if you have a big bang or a big crunch. Classical relativity makes no distinction between space and time. Space breaks down, time breaks down. It's just one thing that breaks down. We could have seen some signs, say in some string theory calculation, that time is somehow singled out from this breakdown and is allowed to survive. And so far that's never happened. There are really technical calculations people like Liu and Freiberg did where they could have found that you can go through a singularity, that amplitudes make sense, that you compute in a setting where in a semi-classical limit what you would be doing is going through a singularity. And they don't make sense. They just fundamentally are nonsensical amplitudes. So that was a chance for the fundamentalness of time to show up in a theory which is so far totally quantum mechanical. So I think the alternative to what you proposed is, well, it's true that string theory is completely quantum mechanical in a setting like ADS-CFT or whenever we've worked with it. One conclusion is, okay, quantum mechanics is truly fundamental. Another is, the reason that string theory has so far not been very successful in describing cosmology or the interior of a black hole at a fundamental level is that it's quantum mechanical. And that we need something beyond that to really understand those regions well.
The idea that Sean was giving was that entropy, according to the later Boltzmann, is related, roughly speaking, to the size of the macro state in the phase space, the appropriate notion of size. The system itself doesn't know anything about probability. It's just obeying Newtonian laws of collisions, let's say, in the case of the kinetic theory of gases. To give you a sense of sort of an analogy, I think of Australia. Most of Australia is covered in the desert. Does that make it probable that you will find people in the desert? It does not. So the phase point in the phase space will meander into the largest areas if the dynamics is right.
what you must not forget is that the very definition of a single configuration crucially depends upon the notion of space. Its spatial relations define, you cannot define one point in a configuration, one configuration without a notion of space. And therefore, I believe the configuration space is not abolished just because...
That's just wrong. You can do quantum mechanics on any space. It doesn't have to be physical space.
I was talking about the concept of a configuration space and not necessarily about quantum mechanics.
I'm just biting my tongue. I have responses to all these things, but I want to get people a chance to say something.
I mean, it seems to me that if we want, we can just rephrase Sean's question in a way that doesn't make explicit reference to any probability distribution. We could say, why was the initial state of the universe, fairly unentangled? Or looking not at the quantum state, but just at the macroscopic features, we could say, why do those have low Kolmogorov complexity, whereas later on there was higher Kolmogorov complexity? And if we do that, then it sort of seems similar to any other why questions that people ask in physics. Why are there three large spatial dimensions? Why are there three generations of particles? I think for each of these things, there might not be any deeper answer, right, but then maybe there is.
Good. I agree completely.
That's fine.
I agree completely.
Does anyone want to propose a new law of thermodynamics relating complexity to entropy?
I'll think about it tonight.
You'll think about it. Good. That'll be a contest we'll have tomorrow.
It wouldn't be thermodynamics.
It wouldn't be thermodynamics. That's true. We still call it that. It's a label. Any other questions? Oh, sorry.
So there is an error of time if you want built into the construction of even physics, which we know now.
Yeah, so this is a good point for those of you who didn't hear it. There is a symmetry, or a would-be symmetry, in operation in particle physics called time reversal, T. And it is violated by the real world, by the standard model of particle physics. But I would not say that we should call that an arrow of time. I think that what I was calling the arrow of time is really fundamentally based on irreversibility. And the standard model, even though it violates T-symmetry, is perfectly reversible and unitary. So I think it's a different mystery that unfortunately the names get entangled with each other a little bit. Yes?
Well, it's hard to know where to jump in. So maybe one place to jump in would just be with a very famous experiment, at least famous to me as a biologist, going back into the 1940s. And it refers to something I mentioned earlier, which is the randomness of mutations. And so I don't know quite where I'm going with this vis-a-vis your question, other than that I don't know how many of you know this experiment. It's by Luria and Delbruck, a biologist and a physicist. It grew out of a really fascinating experiment. It predates the discovery of DNA as the hereditary material. People in biology, and in particular in microbiology, still was a bit of a stronghold of non-Darwinian thinking, what we might sort of loosely call Lamarckianism, the idea that organisms are somehow pushing themselves in certain directions rather than relying on differential survival and reproductive success. Anyhow, in microbiology, experiments were done where a culture of bacteria could be treated with something like a virus that kills bacteria, or antibiotics, or something of that sort. And microbiologists had frequently observed that that the next day or a week later they would come in, the bacteria would now be resistant to the selective agent. And the question was whether that was because there was some low probability of a transition, and you saw the survivors that had then replicated and multiplied, or alternatively there was some also perhaps low probability of mutation that could have occurred at any point in time, but through the sort of propagation of division of cells created a different sort of distribution. So the biologist Luria had been trying to measure this sort of hypothetical rate of mutation, and he found that his experiments were very irreproducible. So again, it comes to sort of probabilities and so on. He had some sort of, I think, flashes of insight, but it was only in talking to the physicist Delbruck that they realized they could do an experiment, which was to grow up a large number of bacteria in replicate cultures, each one starting from a very small, an initial state is, I think, an important issue here, starting from very few cells that are presumably all the same. As they grew outward into large numbers, then challenge each one of these replicate cultures with different, with the same selective agent, and count the number of survivors. And you could distinguish whether the mutation had been induced by the selective agent because it would have a Poisson distribution, versus if the mutations had been occurring all along, hence some of them in the past, the number of events might be Poisson distributed, but the number of countable objects that would come outside the experiment would have what was called a jackpot distribution. You'd occasionally get these big deviations. Right. So it's just a beautiful experiment. It established sort of a causality that is just, it set off the molecular biological revolution. It deals with these issues of predictability and repeatability and the order of events in terms of our inferences for thinking about these questions from a biological standpoint.
We've been arguing about whether or not it's fair to say the universe looks surprising to us. Do you think we should be surprised that life arose?
So we had, I think, a slight version of the discussion as we were coming in from the airport together the day before yesterday. So I think, to me, the kind of answer I would give is it's something that either happened just once or many, many times. So in some sense, I would be surprised if, given the answer, it was 3 or 17. So I don't have a strong opinion about one or many. I guess I'd favor many, but it's one of these questions. What makes something surprising? I mean, why should that be surprising? I don't know, but it just would be, I guess. Something about the numbers involved.
It has not been at the center of memory research, but there is a fundamental distinction between sort of what we represent in consciousness, so like working memory, and then sort of thinking about what's gone from consciousness, and then as one's gone from consciousness, and then we recollect it in the past, right? So basically, the roughly immediate present being one type of memory, and very, very different, and obeying very different principles than long-term memory. And it absolutely is the case that little children have very poor long-term memories, and basically their ability to represent the past in any kind of way, and also to even think about tomorrow and what tomorrow might mean, and what if they were to go on a trip, on a car trip, what they might want to pack with them, what they might need, just have no ability to do so. And I mean, there are a lot of people who do study that empirically. I think a really interesting observation. But basically, the ability to project forward and the ability to recollect both come online at about the same time. And people have suggested that it's a type of consciousness that emerges around 5 or 6 years old.
All right, we're running low on the subject of the conference. Thank our distinguished panel very much.